So welcome everybody to another edition of the OpenXLA community meeting. For February, we've got two awesome topics for you. The first one, we've got the Intel team, along with the Google team, that they're going to be presenting the work that they're doing around XLA CPU. And then after that, we'll spend about 25 to 30 minutes on that. And then after that, we'll talk about the OpenXLA product roadmap for 2025. This was an ask that came out of several folks that attended the November OpenXLA in-person meeting. So wanted to make sure we were addressing the feedback that we got. And with that, I'm going to turn it over to the Intel team and Sandeep from Google to talk about XLA CPU and quantization.
Hi. Yeah, thank you for the introduction. Hi, my name is Nyak. I will present the work of our team at Intel and our collaborator from Google on XLA CPU quantization support. So just to provide background on the XLA CPU quantization workflow, the first step of our pipeline is to convert a TensorFlow AP32 graph into a quantized graph using Intel Neural Compressor, which we call INC. So INC is a library that implements popular compression technique, including quantization across mainstream framework like TensorFlow and PyTorch. So INC will take a TensorFlow AP32 same model or a Keras model as input and generate a new model by inserting the uniform quantize and dequantize. We call it QDQ node immediately before the compute intensive operation. So currently we support the matrix multiplication and convolution operation. And during the calibration process, INC will determine the optimal quantization parameter, which is the scale and 0 point, and store them as a constant node in the graph. This ensures that the QDQ model maintain high accuracy. So for example, in the provided QDQ model diagram on the right, the QDQ nodes are inserted for both the activation as well as the weight input of the mapmo operation. And once the QDQ model is generated, it is passed to the XLA backend. And during compilation, the XLA match the QDQ button and rewrite the corresponding compute-intensive operation to be done in A, which will bring computational benefit on supported Intel CPUs. Next slide, please. So at a high level, we have the TensorFlow model, which will be quantized by INC using both training quantization mode. And the QDQ TensorFlow model will go through MLIR-based TF to XLA to generate a stable XLO with the equivalent stable XLO uniform quantize and uniformly quantize operation. And then the stable XLO will be lowered to XLO, where the QDQ button matching and the rewriting to in A operation happen. So please refer to our RFC and the OpenXLA community talk in July for more detail on our approach and implementation. So for this talk, I will focus on our recent progress in enhancing the XLA quantization support on CPUs, including the new feature that we have added, as well as the performance result achieved when running several popular deep learning model on Intel Xeon CPUs. Okay, next slide, please. Yeah, just to illustrate how we can use INC ABI to quantize model. This is an example of quantizing ResNet 50 Keras model with INC ABI. So first, we will load the TensorFlow AP32 model from Keras and export it as a safe model. And then we need to specify the both training quantization config with the appropriate backend, and then we use quantization.fit to run the calibration and the compression algorithm. So this process will automatically determine the optimal scales and 0 point for inserting uniform QDQ node into the graph, ensuring that we have good accuracy. Finally, we can save the resulting model back to the same model format. And this is important because it's allowed user to continue to use their inference script with very minimal modification. So we are working on upstreaming this QDQ support with the target release by the end of this quarter. Yeah, next slide, please. Yeah, now to the first main enhancement feature. We work on fusion optimization, which we probably all know is a critical technique for boosting the performance in memory-bound workloads, which is common in transformer-based model. So in our XLA CPU optimization, we already have support for this fusion when we run compute-intensive operation in high precision data type like bflow 16, AP16, and AP32. And this include common operation like BIOS add, and activation function like ReLU and sigmoid. So with our quantization implementation, we can easily take advantage of these same fusion optimization when running compute-intensive operation in A. And this integration only requires a small amount of code change in the XLA code base. So you can look at the example here. We have the bias and the bias add and the ReLU have been fused into the in-A convolution custom call. So our approach will allow in-A workload to benefit from the highly optimized fusion strategy that already presented in high precision data type, and thereby enhance the performance without significantly change to the XLA code base. Next one, please. Yeah, so to the next enhancement. So with the base implementation, we have AP32 fallback as default. That means the compute-intensive operation are done in A, but the remaining unsupported in-A operation are done in AP32. For example, here we have softmax being done in AP32, and the in-A matmore custom call is being done in A. But for some model to achieve the best performance on Intel CPUs, it's best to execute non-in-A operation in bflow 16. That's why we next
Next slide.
Yeah, next slide. Yeah, that's why we implement the integration of bflow 16 fallback in our in-A quantization workflow. So Ultimate Precision combine 16-bit and 32-bit floating point type during training or inference to accelerate computation and reduce memory usage. And the official TensorFlow already support the Ultimate Precision with Intel optimization enabled by default. So this means that model running with Ultimate Precision can achieve significant performance gain, especially on Intel processor featuring Intel AMX support. So to enable in-A quantization with bflow 16 fallback, a user can simply add a line of code, like right here, in their inference script. And then under the hood, TensorFlow Ultimate Precision will insert additional cast operation into the computation graph. And as a result, when the graph is lower to XLA XLO, you will notice that you have some extra convert instruction, like in example here before the matmore and after the softmax, and that is all. So that line of code is all the user need to do. On XLA side, we extend our pattern matching to recognize and handle the extra convert instruction, and then we will rewrite the pattern to have the custom call being done in A as expected, and the softmax still being done in bflow 16. So this allow the in-A workflow to benefit from both the in-A computation as well as the outer mid-precision optimization. So in our benchmark, we saw that this enhancement significantly improve our model performance over pure in-A with AP32 fallback. So they ensure that the model can leverage the performance benefit from both in-A and bflow 16 without sacrificing accuracy or requiring a lot of change from the user on their inference scripts. Next slide, please. So yeah, and another enhancement that we implemented is to enable longer chain of in-A operation. So converting back and forth between higher precision and a lower precision can introduce unnecessary overhead. And in many transformer-based model operations such as reshape, transpose, big cast copy, which are generally considered data movement operation, can be performed directly in A with a condition that these operations occur between two consecutive contraction operation like matmore or convolution. And we can do this without accuracy degradation. Therefore, we extend our pattern matching to support the requantization semantic for compute-intensive operation whenever possible. If you look at the example here, we have a big cast and or copy and another big cast and copy between two custom call. We can enable the custom call to have requantization semantic, meaning you have in-A input and in-A output. And in that way, we can remove the quantize in the middle. And that in our benchmark, this optimization proved to improve the performance because we don't have to convert back and forth between high precision and lower precision. Next one, please. So I will show the result that we got on Intel 4th generation Xeon processor, codenamed Sapphire Rapids. It is the first Intel CPU to support the AMX, which are designed to accelerate metric-heavy workloads such as those in machine learning. So in addition, it offers native bflow 16 support, so it can further boost the performance of deep learning application. So in our benchmark, we run 4 model on this processor, vision transformer for image recognition tasks, YOLO V5 for object detection with the mean average precision at IOU equals 0.5 as the metric, and but large on SWAT data set for question answering tasks, and Serena 50 for image recognition. So our results show that the accuracy difference between the in-A model and the FP32 model is very small. However, we achieve significant speed up using our in-A model. See, for VIT can have more than 3 times speed up compared to the FP32 model, and the other model we can achieve almost 2 times speed up. So this already this has been benchmarked on our internal branch, and we will upstream these internal PRs. Also, we have public PR that have been approved on both TensorFlow as well as XLA branch. Next slide, please. So, yeah, just to conclude, we show that running XLA CPU quantization can significantly boost the performance over PU FP32 or bflow 16 with negligible accuracy loss. So in the future, we will plan to enhance our pattern matching to support the quantization for a wider set of model. Also, we observe that the performance of A with bflow 16 for back is better than bflow 16 in general, but there's still some room for improvement. So we need to still working on that. Also from Google, they were working on simplifying the pattern matching with XLO composite, and we will continue working with them to enable CPU quantization support for model written in Jack framework. And I will hand over to Sandeep to talk about the last 2 points.
Thank you, Nat, for sharing these wonderful results. This is really satisfying. I'll go to the next slide. Yeah. So yeah, next in the next 2 slides, I would like to discuss some of our planned future collaborations. So as Nat has already mentioned, this is the simplified view of the compilation which is currently employed to convert the TF model to HLOIR. So is there a question? Okay. Just to reiterate, so we start with the TF float model. We use the ink quantizer, use PTQ mode to quantize it to TF model. It has QDQ hints to quantize different operations, specifically the compute heavy operations. Then we use the MLIR bridge to convert to stable HLO with quantized dequantized operations. And we use a pass, which kind of converts these quantized operations into integer math operations so that they can be converted to HLO. So the key point I would like to highlight here is that the stable HLO QDQ operations are eventually decomposed to integer math in HLO. However, in the HLO, such decomposed operations are recomposed using pattern matching to recover the QDQ operations to be fused with the other operations like convolution, bias, add, ReLU. This pattern matching to identify QDQ is a bit brittle and susceptible to change with any minor changes in the decomposition. To mitigate that, as Nat has already touched upon, is that we propose to simplify the process by translating the stable HLO QDQ operations to HLO composites, which can be readily identified by the pattern matching, making the process more robust and less prone to errors. And the next slide, please. So yeah, we are also planning to experiment with quantizing JAX models to target XLA CPU. Specifically, we would like to use the JAX float models and quantize them using some JAX framework level quantizer. As you can understand here, that one important missing piece is the JAX framework level quantizer here, which will help quantize the JAX models. Now, Google is internally developing such a quantizer, and it will be open sourced pretty soon. The exact timelines will be communicated as soon as possible. However, we are conducting initial prototyping work on the JAX quantizer, and the results are really promising. And we'll share it pretty soon with you all folks. So with that, I will conclude the presentation, and feel free to have any questions you have.
Perfect. So let's open up the floor for any questions. We've got about 9 minutes, so plenty of time for questions.
I think the JAX quantizer is a fantastic development because it will strengthen the JAX's story for inference. Right now, I feel like it's kind of a little weak. So as soon as you can have those timelines, it will be fantastic if you can share that. And I had a question for Nihat. So Nat, how much of your work is actually back-end agnostic, and how much it is very specific to CPUs?
Yeah, I can go. And so this is Mahmoud. I'm also working with Nat. So we are relying on one DNA library that is, for now, it's CPU. It's dependent on CPU, but But the pattern matching, because a lot of the work is also dependent on the pattern matching, that can be easily generalized and used for other backends as well. Although right now it's under service CPU directory, but it can be easily generalized to support other backends. But since we are relying on 1DNN, we assume 1DNN is library is there, and we target CPU for now.
Thank you.
Any other questions?
Don't be shy. Okay, all right, I guess not. Then I'm going to turn it over to Chris. I'll stop sharing, Chris, so you can share your slides to talk about the OpenXLA product roadmap. This is what folks during the November OpenXLA Dev Labs were asking for, and you requested it and we listened. So Chris, I'm going to turn it over to you.
Great. Good morning, everyone. Thanks to the Intel team for the presentation. I actually got my Intel waddle here, so love it. So let me go ahead and share my screen and we'll get started. Okay, let me.
And Chris, you're
Cool.
off camera. I'm not sure.
Oh, I have it going from just my laptop,
Okay.
but I guess it must be. I'll just do the one from the conference room. Okay. All right, looks like we are good to go. All right, so for those who haven't met me, Chris Jones, the new product manager for OpenXLA at Google, started at Google in December, so still very much onboarding to the team. But I'm going to go over the roadmap we have. A lot of the focus is going to be on Q1 and H1, and there was going to be some H2 items in here. So what we have here is, this is what I'm going to be going over, is we'll start with stable HLO. We'll go into XLA CPU, XLA GPU, Shardy, and then OSS infrastructure. So, we really have a couple of goals for stable HLO. The first one is we really want to maximize the benefit of stable HLO for the entire OpenXLA community. We also want to unify the developer experience for all OpenXLA members. So the first item we have here, MHLO deprecation and migration. And the reason we're highlighting this is that, the core motivation here is we want to eliminate greater than 90% offset redundancy we have between MHLO and stable HLO. Maintaining two almost identical dialects, it's inefficient and it's complex. So to address this, we've already started migrating useful passes like canonicalization and folder patterns over to stable HLO. The next key is going to be to issue an RFC for external migration timelines in Q1. The RFC will detail a plan and support for migrating the MHLO-based projects to stable HLO. So, we are committed to, we know that this can be a lot of work, so we're committed to providing ample timeline and resources to support teams during this transition throughout H1. We think that this move is going to simplify the compiler stack and allow us to kind of focus our efforts on a single stable dialect. Next item, migrate hardware independent optimizations to stable HLO. Our goal here is to consolidate the hardware independent graph simplifications in stable HLO. So this means making stable HLO the central place for optimizations that benefit everyone, regardless of the specific hardware target. So by doing this, we benefit all the PGRT plugins, including those that convert from stable HLO to even non-XLA compiler IR. So, this benefits, this kind of ensures broader access to these valuable optimizations. This work will consolidate optimization patterns from various projects, and this is going to be a key focus for H1. Getting into, we'll talk about quantization. So this is going to be H1 and then, but probably starting in Q2. So we're making significant progress in this area. We have an RFC for subchannel quantized types. It's currently in review, which is a crucial step for efficient quantization. We're also actively exploring JAX quantization framework integration. We want to create a smooth and standardized path for quantized models originating from JAX to be represented and optimized within stable HLO. We plan to share the JAX integration results probably in Q2, so stay tuned for updates on this. Next item, we have composites end-to-end. We've seen pilot projects using composites with GRAD, VMAP, sharding, and we're working to ensure composites work in complex workloads. Composites are a really powerful way to represent higher level ops in stable HLO. They promote flexibility and extensibility. By ensuring they work seamlessly in various contexts, we're paving the way for making composites the default and preferred approach for targeting high-level ops in the OSS ecosystem. We'll jump into OpenXLA CPU. I really think I would say our focus is kind of three things. Performance, modernization, and unification would be the three. So the performance improvements are immediate. We're targeting a 20% runtime speed up and 40% faster compilation. These are significant efficiency gains, I think, making CPU a stronger target. Improvements will come from optimizations across the pipeline, enabling our componentization efforts. Next one in H1, new code gen based on XLA GPU's kernel emitter. So we're going to be adopting the GPU kernel emitter for CPU, and this allows us to share some of the compilation passes for non-reduction ops, reducing duplication. So this enables sub-byte code gen for quantized models, and we're seeing about a 50% performance boost for complex fusions, and this addresses a major bottleneck. This modernizes our CPU code gen infrastructure and aligns it with componentization. So library integrations. So we think these are also going to be pretty critical for CPU performance. We're prototyping X and N pack integration. This adds BF16, int8, int4 support for optimized kernels. We'll modularize and expand one DNN integration, utilizing the Graph API for better fusion. We'll also build shared fusion passes for libraries to intelligently leverage them based on performance. And then component unification with XLA GPU. Really this is about kind of collaboration, and we'll unify code gen and collective APIs between CPU and GPU. It's going to simplify development, and we think it's going to reduce code duplication. So we'll also create a shared kernel testing library for better quality and consistency. Our goal with OpenXLA GPU is to deliver state-of-the-art GPU performance for the entire OpenXLA community. This is across both kind of open source and general machine learning workloads. Our strategy focuses on modularity, really leveraging the power of Triton Code Gen, integrating key libraries, and collaborating with hardware vendors. So specifically into Triton Code Gen. We're really investing heavy in this area, and we see that this is going to be our core kernel generation technology for GPU. We're migrating to a generic Triton emitter for broader operation coverage. This includes key dot fusions and removing older emitters for simplicity. This unlocks TMA loads and stores for efficient memory access on modern GPUs. Multi-output fusion and fusing normalizations in Triton will create a more powerful and performant kernel for everyone. Triton is key to achieving peak GPU performance in OpenXLA. So we also have a new auto tuner and streamline compilation, and this is really going to be about performance and stability. So we're building a standalone, back-end agnostic auto tuner for GPUs. This tool will optimize kernel parameters for different libraries and emitters using profile-guided optimization, or PGO, for best real-world results. This makes GPU compilation deterministic improving reliability for users. We're also going to be splitting XLA GPU into a separate compiler and runner for better code optimization and future extensibility. This new auto tuner ensures consistent high GPU performance for all OpenXLA users. And continuing on OpenXLA GPU, we've got tunable emitters. This is focused on maximizing performance, and we're making XLA emitters tunable and integrating them into our new auto tuner. So this is going to allow even finer control over kernel generation and performance. This also enhances flexibility, and it enables us to seamlessly integrate with other backends, like Triton itself, if needed. Last item is horizontal scaling. So, here we're really focused on horizontal scaling optimizations for very large distributed models. So this includes SPMD pipeline parallelization, the NVIDIA shared memory integration for fast multi-GPU communication, and better cost modeling for latency hiding scheduling. We're also adding ragged tensor support. I know this one comes up a lot for collectives in MOE models and exploring parallel collectives on multiple streams. So these horizontal scaling efforts ensure that OpenXLA can handle the largest and most demanding AI workloads and GPUs. Getting into Shardy. First item here is seamless integration for JAX exporting. We want to make it really easy for JAX users to benefit from Shardy. So this quarter, we're going to ensure full support for JAX export with Shardy enabled. We're also adding compatibility tests to guarantee a smooth and reliable experience. For JAX users, this means we can leverage Shardy's advanced partitioning with minimal effort. Effectively, it's just kind of flipping a flag in your JAX code. So for compatibility, Shardy is really built on a core component of XLA. So seamless integration is really going to be key. So this half, the effort is really to ensure full forward and backward compatibility for Shardy across the whole ecosystem. Specifically, we're working to support interleaving Shardy and stable HLO ops in your programs. This means you can confidently use Shardy alongside other OpenXLA tools and dialects, knowing they're going to work together reliably and consistently. Explicit reshards and AXI-based collectives. This is really more focused on, I would say, enhanced debugging and performance. It's about making distributed programs easier to understand and run efficiently. So we'll be inserting explicit reshards in the compiled code, making data movement much clearer. Then we'll convert each reshard to a sequence of AXI-based collectives. This approach has two key benefits. First is improved debuggability, because the communication steps are explicit and visible, and improved performance by allowing us for more optimal resharding strategies. This will help address some of the limitations of older partitioning systems like GSPMD, and ensure Shardy delivers both usability and speed. Getting into OSS infrastructure. So the first one is componentization. I know I've heard this requested a number of times, and we're really working to on OpenXLA componentization, and this means we want to create dedicated components within the XLA code base, kind of similar to how stable HLO is organized. We'll also be moving backends behind PGRT plugins for better modularity. This makes the code base cleaner and easier to navigate. This is really important for new contributors who want to get up to speed quickly. We're building tooling and documentation for testing and debugging HLO passes, and aiming for high code coverage, hopefully above 90% within these components. Componentization is about making OpenXLA more modular, maintainable, and contributor friendly for long term. Documentation, we fully get that documentation is essential to a thriving open source project. We've already added documentation for Shardy. We've revamped it for XLA and for stable HLO docs. This is an area we're going to contribute more, and we've got budget and resources and able to do that more this year. So this will really be a real concerted effort for us. Feedback is really critical. We need to know what documentation is working, what documentation you need, and how we can improve it. Or if you even want to contribute to the documentation. Single host benchmarking. So this is about kind of preventing regressions and ensuring performance. We've established automated and standardized benchmarking CI for XLA CPU and GPU. This helps us prevent performance regressions and ensures that OpenXLA remains fast and efficient. We'll have continuous performance tracking so we can monitor changes and catch issues early. The benchmarking infrastructure, it's about maintaining the improvements, maintaining and improving the performance you rely on in OpenXLA. Kind of continuing that, what we're doing is building on kind of that single host benchmarking. We want to develop extensible benchmarking infrastructure. This is going to enable OSS users to effectively onboard and compare your benchmarks on various hardware platforms. We really want to make it easy for you to measure performance and contribute your own benchmarks to the project. The next item is OSS CI. So we're moving our CI to GitHub Actions to be more open and transparent. We're making TensorFlow builds to our CI, kind of similar to existing JAX builds, and this will broaden test coverage. We're also making files writable via PR to ease contributions, with some exceptions for third-party code and core tooling. This CI effort is about making OpenXLA kind of really open and collaborative project on GitHub. And our last item here is OpenXLA releases. We're committed to providing tagged and validated XLA GitHub releases with release notes and performance benchmarks. We'll also provide pip install XLA CPU GPU plugins. This right now we're working on kind of the proposal for what OpenXLA releases right now. So hopefully we'll have something relatively soon. That's it for me.
Awesome. Thank you so much. All right, so let's open up the floor. We've got about 6 more minutes, so we've got time for questions. We also have Kevin from the Stable HLO team if you've got specific questions around Stable HLO, and Penpan's here as well to talk about XLA CPU. Cyril.
Hi, yes, I was wondering if you could share any plans around PGRT API. Do you plan to evolve it, change it in some ways?
Yeah, do we have anyone? Kevin?
Kevin's here, yeah.
Maybe you take this?
Yeah, I don't want to speak out of line because I'm not the one who's doing the plans, but people are actively looking into what a PGRT v1.0 release was. I'm not sure on timelines or any of that, so that might be future community meeting, but that probably should be included here.
I'll make a note to include it in one of the future community meetings so we can detail that out a little bit more.
Cool. Yeah, thanks for flagging that.
Thank you, Cyril. I think we've got one more question, don't we? Anyone else?
One kind of maybe detail. So we can already see some PRs, etc., around moving to GitHub Actions, etc. But this testing and all that is still gonna. And I noticed that the testing is using PyTest, not Bazel. Is that deliberate, or is it like a temporary arrangement until we figure something better out through Bazel? Maybe it's a DevOps question, maybe too specific. I can reach out in the channel and maybe get some clarity. Yeah, that's okay. But
I can see people.
I'm sorry?
I said I think that's the right way to do it. I'll CC in the right people who are actually working on that migration.
Sounds good. Thanks.
Thanks.
Any other questions? Jaya?
Yeah, just curious. So when you move to GitHub Actions for OpenXLA CI, what is the user visible impact that we can expect to see? Is there any what changes for us from our side? What can we expect to see if the CI moves to OpenXLA or GitHub Actions? Anything you can share on that?
I think in general, and again, this is the same person is who I would CC into both the past two questions. So maybe also we can take this one more publicly. But I think the user side will just be more transparency. I don't think we're introducing very much new stuff. The old infrastructure used to be that we like run a build on, I think, Google machines more internally, and I don't know how public the logs are. Now it's all of the logs are in GitHub Actions. We're really just migrating build scripts, I think, from internal infra to GitHub Actions.
Got it. Okay, so that would, yeah, that would definitely be a plus if there is more logs available or visible now. Yeah, thanks.
I think we're going to have to probably do is put together some docs on this. I think we're going to really need is just a clear document for for everyone to be able to know exactly what's going to be impacted, how's it going to work, how do they do it going forward, who do they reach out to for support. So Aditi, maybe we can have that as a takeaway.
Yeah, for sure. Thank you, Jared, for highlighting that. Okay, we got 2 more minutes, so probably can do one more question. Kandukar?
Yeah, I don't have any question, but I'm really excited to see the roadmap. That was really well planned. Thank you for doing that.
Of course. Awesome. All right, great. Thank you, everybody. We will reconvene next month. Thanks for everybody for joining. Bye.
Thank you.
Thank you, folks.
Bye.